This video is my last demonstration of how easy it is to program advanced and scary capabilities into drones and robots. In this video, I will demonstrate how easy it is with approximately 110 lines of code for a processor to automatically detect a simple target in a high clutter environment and then detect and guide a laser beam and determine when the center of the laser beam is centered on a target, meeting a minimum target requirement of several pixels. At the end of this video, there's a wall of words. I apologize. I promise I will not read them to you. But, big but, if you are even casually interested in the capability of widely available technology, you should read the last 3 slides and follow the logic. Think about the description of the capabilities and compare these thoughts to my other videos as described. So, moving on. This is a picture, a rendering of the experimental setup. There is a simple computer. There is a simple webcam. It's a Logitech. It is a high-definition webcam. There is a laser, a green laser pointer bought from Amazon. There's a piece of blue plastic that I used as an optical density filter, an OD filter, to attenuate the intensity of the laser so it did not saturate the camera. And there is a simple target usually used in target practice, target shooting. You notice this is a very high clutter environment. So I used a high clutter environment. It's actually my man cave where I play with my toys and my projects to test the capability of the hue circle transform method to find simple geometric shapes. In this case, a circle. So the hue method basically takes a color photo, turns it into a grayscale, blurs it, and then looks for the geometric shape. In this case, a circle, where you also define the radius of the circle that you were attempting to detect. Then in the code, we highlight the detected circle with the green outline, and we place a red dot at the center. For this to work, I had to find the maximum camera resolution. So here's some simple code, courtesy of the internet, to find the camera's resolution. And then at the capture of each frame, you have to set the resolution in Python so that it captures the full resolution and uses the full resolution of the video frame. This is just a low light example. It was starting to get dark and I didn't turn on lights, and I was interested in seeing how well these algorithms performed in low light. And as you can see, it again easily found a circle and drew a red dot, placed a red dot at the center of the circle. If the laser's too bright, it's going to look white. Now you can program the algorithm so if you see white surrounded by green, to assume that it's actually green and the camera's saturated. In a sophisticated system, the camera would have automatic gain control. Again, you could program it that if it sees green encircling white, to reduce the gain to determine if the white is actually a green image that is saturated. In my case, I employed a cheap piece of blue tinted plastic, used it as an OD filter to attenuate the laser beam. Since the detection algorithm is looking for green, I did change the Hogue programming algorithm code so that instead of finding the circle and coloring it green or highlighting it in green, to when it finds the circle, highlight it in blue, so that adding green to the image would not detract from the algorithm to find the green laser beam. Here's a close-up. It shows the diverged laser spot. It shows the blue highlight of the circle that is detected. It shows a red spot that is the center of the detected circle using the Hogue algorithm. It shows the green laser beam that has been attenuated and diverged by a blue piece of plastic. And it shows where the algorithm has calculated the center of the laser beam, which in this case is 7 pixels between the center of the red and the center of the yellow, which is within my targeting requirement that I program, which is plus minus 12 pixels. By the way, the entire cluttered picture is 23 by 04 by 1536 pixels, which is why even in this image to the right, it looks like the red and the yellow is separated. Is actually only 7 pixels. Now, the examples that follow are just more examples of the detection of the circle, the green laser beam, and the centers, and when it meets the required capabilities. A lot of drones are controlled by man in the loop for a lot of reasons. Number one, the U.S. has the capability to control drones over great distances, which requires wide bandwidth and great communications. And then a man can make decisions about about firing a weapon or not, and also then use his cognitive capabilities to determine the adequacy of the target lock. Developing nations, independent, nefarious organized groups, in other words, terrorists, with some expertise would find it easier to produce a fire and forget weapon using the techniques I described in this video and in the summary at the end of this presentation, which covered all my previous videos. So again, examples. So here you see the green laser diverged circle. You see that the yellow is the calculated center, the blue circle, the Hogue target detection, circle detection with the red dot for its center, and in this case, they are only separated by less than 12 pixels, so the center of the laser is shown as the yellow dot. Example, previously we talked about if the laser is too bright. Lower left, we show where the attenuation was too great, and yes, there is green, but it looked like a very dark green, which was slightly outside the pixel values that I programmed for green detection. Easily a camera with automatic gain control, you could program it that if it sees dark green to raise the gain of the camera to determine if it's actually the green laser which you are trying to detect. In this case, I just reduced some of the attenuation, but just like if the laser's too bright, you have to use automatic gain control, and if the laser's too dim, you have to use automatic gain control. This simple demonstration, I just use filters. Another example, it's interesting that the TV in the background, watching Jeopardy, good pastime, but image in the background did not detract from the detection of the circle, the center of the circle, or the green laser beam. So it was rather impressive that those simple algorithms are so robust. In this case, the beam was not centered on the target. The green laser was not centered with respect to the blue circle adequately. It was approximately 13 pixels. The requirement was 12, so it drew a blue dot. Now, the blue dot's not where you at first glance would draw the blue dot. And that's because if you look closely, there's a lot of green scatter all around the central beam. So the computer's algorithm did the calculation, and decided the center is where the blue dot is shown. Many discussions while I was still employed with laser engineers who thought they always knew what a seeker would see, what a camera would see, what the automatic gain algorithms would produce, and then what the algorithm doing the image processing would assume as far as the center of the beam. They just were very headstrong, let us say. Another example, again, different TV image. By the way, I moved the laser beam. You can see it has moved. Someplace in there, there's a blue dot, but it's buried in the laser image. Beam's not sufficiently centered. That's why you don't see a yellow dot. And in this case, the error was approximately 14 pixels. Another example, this time it is centered adequately according to the algorithm. Again, we as humans would probably say that's not the center of the laser spot, but with all the clutter and with the algorithm, the yellow dot was placed at the center of the calculated center of the laser beam, and when compared to the red dot, the center of the blue circle, it was less than 12 pixels, and in fact it was 6 pixels. This time I moved the beam and it was right on center, and this time you have a little less scatter, so it did show the center more likely where you would assume the center was approximately. So in this case, you may not be as surprised about where the centers are located. Another example, yes, the major beam's off center. Now you can see a lot of scatter. And again, the blue dot isn't where you would necessarily place it, but the blue dot is where the computer algorithm placed the center of the beam as it saw all the scatter. Perhaps some of it may be that some of the pixels were saturated. I see white in part of the beam here, so the algorithm may have ignored that and did not include that in the calculation. Again, if you had automatic gain control, I'd program the device to reduce the gain, and then again, analyze the picture, because apparently there is saturation. Another example, this one, the beam just happened to be beautiful. There's a hole in the center of the beam, or at least low intensity in the center of the beam, but the yellow dot is where you would probably assume the center of the beam would be located. Again, the TV picture did not distract the algorithm whatsoever. Another example, again, just another example, shows the laser beam off center. It shows the blue dot, the calculated laser beam center, and it shows that since it's blue, the laser beam center and the blue circle center are not concentric enough to meet the plus minus 12 pixel. Now we're at the wall of words. So the next 3 slides are wall of words. As I said at the beginning, I was not going to read these to you. Most of you will not be interested. If you want to understand my message concerning the capability of widely available technology, read these slides and follow the message and the logic, and compare these thoughts to this video and my other videos as the wall of words describes. This concludes my description and examples of my widely available technology as applied to drones and robots. There's no reason for me to continue along these lines. I have no intention of making a tactical device. This does demonstrate, if you read the wall of words and follow the logic, all the constituent parts that are needed to build an autonomous drone that can fly independently based on GPS coordinates, detect a unique programmed object using YOLO, object definition as described in my other videos, using YOLO then for the custom object detection, using then the image processing to detect the laser, which if it's on a gimbal platform, you could close a servo loop on the laser platform to put the laser center on the center of the target as demonstrated in this video. So I'm done with this exercise. My point was to show how easy some of this is actually in today's world. I did mention someplace in here that large aerospace companies spent years in the 80s and 90s and early 2000s and millions of dollars developing some of this capability. Now it is very widely available and easy to implement using bits and pieces of code that are widely available on the internet. So, like I said, I'm moving on. I'm going to be specializing in generative adversarial neural networks and graph neural networks. These are two of the hottest areas in neural network research at this time, since they are very hot, very groundbreaking. No one actually knows how good they are or what they can actually do. So I hope to indulge in that to some degree.